All right, so chain rule. The reverse of the chain rule is U substitution. So U substitution is exactly what it sounds like. It's substituting a variable in terms, not a variable necessarily, but an expression and rewriting it in terms of a different expression. So that seems pretty self-explanatory. Let's just do it without going to calculus. Let's say that there's f equals 4x. Let's just say that u is equal to whatever of x. It doesn't matter. You can say it's equal to x squared, in which case then x would be equal to a certain ratio of u. And let's solve for u here, and then we get x equals square root u. So plugging it back into the expression, we get f equals 4 square root u. And if we're to plug u back in, we get the same exact thing. So if we plug back u, we get 4 square root x, which is equal to 4x. Obviously with some nuance, because if x is negative, we have some problems. But it wouldn't be negative here because, well, yeah. Well, this is how it works. But there are some cases where if you're not doing it in terms of calculus, and you're not denoting u as a independent variable, and you're saying that u is a fixed constant, then this could provide some errors. Not in this case, obviously, because we are saying that u is just simply a resultant of x squared. So essentially what we're doing is we're trying to rewrite something in terms of u. And we can do this a lot of ways. Well, first let's try a simple one. Let's do like x plus 1 squared. If I was you and I was trying to do this simple indefinite integral, all I would do is I would just expand this out, and I would obviously plug in, or not, in this case it's an indefinite integral. I would just expand this out and then apply the reverse power rule. You can do that too. In this case it would be x squared plus 2x plus 1. I don't know why, oh yeah, okay. And then that would be x cubed over 3. So just applying the reverse power rule plus x squared plus x. And we can plug in, like, let's just do 1 and 0. And we'll test if it's correct in the future. If we plug in 1, it'd be 1 divided by 3 plus 1, which is equal to 2.333333 terminating. But we can now, let's just say that for future reference, which is going to that's just 8/3. So we'll save that for future reference, 8/3. So essentially the answer to that definite integral is 8/3. But how do you do so where we don't expand it out? Because it can get complicated. It can get to even the 4th power, and if it's the 4th power, things get a little bit complicated because you can't expand that out. You probably can using binomial expansion theorem, or even Pascal's, I forgot what it's called, Pascal's pyramid. You can use that too. But in this case, we'll just use U substitution. So let's go over the logic of it. U substitution is essentially, again, just denoting a random variable U. You can also say Z, Y. It doesn't have to be anything. They just say U for, I guess that was the notation for hundreds of years. I don't know if it was Newton or Leibniz who discovered it, denoted it. I think it was probably Leibniz because we are using Leibniz notation here. So let's say U is equal to x plus 1. And we're using x plus 1. Technically, U substitution doesn't always work, and there are rare cases where it will not work. But for simple functions like this, I'm sure U sub will almost always work, especially for just a simple polynomial or quadratic like this. So U is equal to x plus 1. So now we could just plug U back in. And now you can see this new thing, and you probably are probably a little bit curious because U and X are not the same thing. In this case, U is always going to be 1 greater than X. So in this case, you might say, well, we get it into this form, can we just reverse power rule it? And you can't, because U and X, of course, are not the same thing. So now you would have to find what dx is in U, just essentially rewriting it. So to do so, we can just say, hey, let's take the function U, and let's differentiate it on both sides. And we're going to be using the concept of differentials here. That's actually not correct. The derivative of x plus 1 is just 1. We're going to use the concept of differentials, which essentially states that you can write du, which is just change in u, as x dx. So a very, very tiny change in dx will always be the same as that very tiny change in du. In this case, it's a linear function, meaning that the rate of change is always the same. So that means du and dx will always equal each other, which is quite convenient. But in other cases, it still works because we're considering a very small change in x, and as dx goes to 0, du goes to 0, no matter what the relation is, typically, unless it's like a reciprocal relation, which it'll never be because you're multiplying dx on both sides. So essentially, du and dx, it doesn't matter if it's equal to each other or if it's not equal to each other. All we want to do is find the relationship of these two. And it turns out that even a small change in dx is just equal to du, so we can rewrite it as u squared du as the integral of u squared with respect to du, and you can say, hey, well, we can just use the reverse power rule because it's just an arbitrary variable. Very weird. U cubed over 3 is the answer, and we'll plug in the upper and lower bounds to get 1 and 0, and we'll get 1 over 3. Oh, wait, sorry. Why am I plugging in the upper? Oh, yeah, we're not finished yet. We get u cubed over 3. I was like, that doesn't match up. But we realized that u is just a variable of x, or u is not a variable of x, it's a function of x, so we'll plug it back in, and we'll get x plus 1 cubed over 3. And now if we plug in the upper and lower bounds, and remember we were trying to integrate the variable with respect to x, which is why we have to swap it back in, and we get 2 cubed over 3, and if anybody knows what that is, it's 8 over 3, which is the exact same thing. So it proves that this method always works, or not always works, but it's going to be precise to if we're going to use another method, because obviously you're just anti-differentiating it. So let's try to find another example. I'll just search it up, I guess. We'll do 4x sine 3x squared. So that's the logic behind it. So I'll explain it one more time. One, just to note a variable u equals something of x. So let's just say u equals f of x, which is probably not right to say. U equals a function of x. Actually, yeah, that's right. And number two, finding what a small change of dx is equal to du, and it's usually just going to be a constant, so c du, which essentially just means dx is usually just going to be like a constant. Sometimes it can actually be variable sometimes, so that's not the case, but c is just going to represent a function. So dx is going to be equal to some multiple of du, or even like function of du, function times du, and 3 sub dx back in. And once you get it into the form of u du, or not u du necessarily, f of u du, then you can just use the typical elementary antiderivatives that we've done before, such as like the antiderivative of secant squared x is tan x, and the antiderivative of sin x is sin, stuff like that. So yeah, that is essentially the sub. So let's do one more next problem, and we're going to use the integral of 4x sine 3x squared dx. And I didn't look at the answer, but I guess I could come back to that later. So let's denote u. Again, it's a little bit not foolproof because it's a little bit difficult to like see if the u substitution is going to work and then where to plug u in. Should I say that u is equal to sine of 3x squared? Like, it's a little bit difficult to do so. So you're going to have to use some logic and like pick out like a logical guess in the beginning. So here I'm just going to say u is equal to 3x squared. This means that we can rewrite the integral as 4x sine of u. That's pretty logical so far. So then what is u in reference to x? Well, that means u is equal to, well, I don't know why I did it. I guess I could just do it in my head, but it would be equal to u divided by 3 square root. So all I did was solve for x in this case, and we can plug that back into here to get 4 square root u over 3 sine of u. And this is still in reference to dx because we haven't found the relationship between dx and du. Additionally, you don't have to do this complicated part too because sometimes they will cancel out. Yeah, sometimes they will cancel out, but you know what? Let's see if it will cancel out because this is going to get a little bit complicated. So they will cancel out when you plug in du. So we get the integral of dx or in reference to x. Well, still with respect to x. And now what we're going to do is we're going to find the relationship. So du is just going to be equal to 6x dx, which essentially means that the change in du will always be 6 times the variable x times dx greater than dx. Or no, 6 times x greater than dx. So now we can plug that back in. And first we have to solve for x. So it's going to be dx equals du over 6x. So it's going to be an integral of sine u, and it is going to cancel based off me just reading it. Sine u of du over 6x. These cancel out to give 2/3, so we get 2/3 sine u du. And now this is just a simple trigonometric antiderivative. 2/3 negative cosine u is the answer. And to substitute it back in, we get negative 2 3x squared over 3 to get negative 2x squared. And once we get negative 2x squared, it should be pretty simple from there. 2x. Oh, sorry. Why did I plug in? Oh, yeah. No, sorry. This is the antiderivative. The antiderivative is negative 2/3 cosine u. Oh my gosh. Cosine u. There we go. And now we know what u is, so it's going to be negative 2/3 cosine 3x squared. And this is your answer. Actually, it's not your answer. I forgot the plus c at the end, which is just the constant of integration since we're doing an indefinite integral. So yeah, that's the logic behind there. Essentially, just denote something as u, and yeah, that should be pretty simple. Now, obviously, there's cases where it won't work. Like, if you're watching, you should probably try this integral and try to solve that. But it obviously won't work because this is a derivative without an antiderivative. So it's not going to work here, but yeah, in some cases, substitution won't work, and you can't just do it. So